All right, let's go. Number 10. The measurement problem. In the 1920s, Niels Bohr and Werner Heisenberg were not trying to break reality. They were trying to finish a periodic table problem, working out why electrons don't spiral into the nucleus and radiate away their energy like classical physics demanded they should. Standard physics said a particle has one position, one momentum, one definite state at any moment, whether anyone looks at it or not. That's the setup. That's the rule the entire 19th century was built on. Then the math for the electron refused to give a single answer. It gave a wave of probabilities, a smeared-out ghost of every position at once. And the only way to get one answer was to write a mathematical step called collapse, triggered by something the equations called an observer. Nobody, then or now, has ever formally defined what an observer is. Werner Heisenberg himself wrestled with this in his 1958 book, Physics and Philosophy, and a century of quantum mechanics has been built on a term nobody can define. Every explanation has failed to close the gap. The Copenhagen interpretation says don't ask. The many worlds interpretation says every outcome happens, just in a universe you can't see. Pilot wave theory tries to keep things deterministic, but requires a hidden field influencing every particle in existence simultaneously. Every attempt trades one mystery for another. If observation defines reality, your own present moment is only fixed because you happen to be looking at it. What happens to the part of your life nobody is watching? That mystery didn't stay theoretical. It got tested directly. Number 9. Wigner's friend confirmed. Eugene Wigner proposed his 1961 thought experiment as a philosophical joke. A way to push the measurement problem to its logical extreme and expose how absurd it sounded. A friend measures a particle in a sealed lab. Wigner, outside, treats the entire lab, friend included, as an unmeasured quantum system still in superposition. The standard assumption was that this was just a paradox on paper, that reality itself couldn't actually produce two contradictory facts for two equally valid observers. Then, in 2019, physicist Massimiliano Proietti and his team at Heriot-Watt University in Edinburgh built the experiment for real, using 6 entangled photons to stand in for 2 separate observers and their measurements. They found that both observers obtained results that were locally correct and mutually exclusive. 2 valid, verified facts about the same event that could not both be objectively true. The Innsbruck group, led by Aslav Bruckner, ran follow-up analysis confirming the result wasn't an error in setup. Every attempt to explain it away has failed. Adding hidden variables breaks other confirmed predictions of quantum mechanics. Assuming one observer is simply wrong violates locality, the rule that information can't travel faster than light. Physicists are left holding 2 true, contradictory versions of one event. If this scales beyond photons, the version of what happened yesterday that you remember may not be the only valid one. If 2 people can't even agree on what a photon did, what does that say about the mind doing the observing? Number 8. The Libet Experiment. In the early 1980s, neuroscientist Benjamin Libet at the University of California, San Francisco was not trying to disprove free will. He was studying the basic electrical signature of voluntary movement, a routine question in motor neuroscience. The standard assumption, the one built into every legal system and every religion, was simple. You consciously decide to act, and then your brain executes the decision. Intention first, action second. Libet asked subjects to flick their wrist whenever they felt the urge, while watching a fast-moving clock to mark the exact moment they became aware of deciding. The EEG data stumbled onto something nobody expected. A slow buildup of brain activity called the readiness potential began before subjects reported any conscious awareness of choosing to move. Libet published the results in 1983 in the journal Brain, showing the readiness potential preceding conscious awareness of intention by several hundred milliseconds. Some interpretations push the gap even further. Every attempted rescue of free will has run into the same wall. Some argued the conscious veto still counts as free will, but that only controls stopping an action, not starting one. Others blamed the clock reading method as imprecise, but later fMRI replications by John Dylan Haynes in 2008 found predictive brain signals up to several seconds before the reported decision. The math keeps holding up. Your brain may already be building your next choice, while you still believe it hasn't happened yet. So if the decision is already made before you know it, who exactly is doing the deciding? Number 7. Anesthesia's unsolved mechanism. In 1846, dentist William Morton was not trying to solve the hard problem of consciousness. He was trying to stop patients from screaming during tooth extractions, testing ether as a practical fix for a practical problem. The standard assumption in modern medicine is that we understand our tools. We map dosages precisely enough to control heart rate, blood pressure, and breathing to the decimal point. Doctors stumbled into a strange gap. They can reliably switch consciousness off and back on in an operating room every single day, and nobody can tell you, at a mechanistic level, what property of the brain is actually being switched. Anesthesiologist Emory Brown at Massachusetts General Hospital in MIT has published extensively, including a widely cited 2010 paper in the New England Journal of Medicine, arguing that anesthetic drugs don't simply turn off the brain, but disrupt communication between regions in ways still not fully mapped to subjective experience. Every proposed mechanism has fallen short. The lipid theory, dominant for most of the 20th century, assumed anesthetics dissolved into fatty membranes and disrupted them physically, but it couldn't explain potency differences between similar molecules. Receptor binding theories explain some drugs but not others. No unified account exists. We perform this act of erasing and restoring a person's inner world thousands of times a day worldwide, on faith that it will come back. What is actually being suspended when you go under, and what guarantee do you have that the same you returns? If we can silence consciousness without knowing what it is, what does that say about our confidence in defining it at all? Number 6. The binding problem. In the 1980s, neuroscientists including Christoph Koch and Francis Crick were not trying to solve philosophy. They were mapping which brain regions process which features of vision, color in one area, motion in another, edges and shape in others, a routine anatomical project. Standard neuroscience predicted that if a scene is broken into dozens of separate signals, processed in dozens of separate regions with measurable transmission delays between them, our experience of the world should feel fragmented, arriving in pieces. Instead, every one of us experiences a single, seamless moment. Color, motion, and shape appear bound together instantly, with no seam anywhere to be found. Crick and Koch published a widely cited 1990 paper in Seminars in the Neurosciences, proposing that synchronized neural firing, cells oscillating together around 40 Hz, might be the glue binding these signals. It's called the binding problem, and it remains formally unsolved. The 40 Hz synchrony theory ran into cases where binding still occurred without matching oscillation patterns. Other researchers proposed a single integration hub, but no such anatomical structure has ever been located. Every candidate mechanism explains part of the puzzle and breaks somewhere else. Your entire visual world right now, the screen, the room around it, is being assembled from fragments arriving at different speeds, stitched into something that feels instant. If the seams are real but invisible, what else about your experience is being quietly edited before it reaches you? Number 5. Split brain patients. In the 1960s, neurosurgeon Joseph Bogan and researchers Roger Sperry and Michael Gazzaniga were not trying to study the nature of self. They were trying to treat patients with severe drug-resistant epilepsy by cutting the corpus callosum, the thick bundle of fibers connecting the brain's two hemispheres, to stop seizures from spreading. Standard neuroscience assumed that consciousness was a single, unified process running across the whole brain, and severing a connective structure would simply reduce communication, not multiply the self. What Sperry and Gazzaniga stumbled onto, and published across a series of papers through the 1960s and 70s, work that earned Sperry a share of the 1981 Nobel Prize in Physiology or Medicine, was stranger. In carefully controlled experiments isolating information to one hemisphere at a time, the left hand, controlled by the non-verbal right hemisphere, could select objects or perform tasks the verbal left hemisphere had no knowledge of and would then confabulate explanations for. Two systems, in one skull, capable of independent decisions the other wasn't aware of making. Every attempt to file this away as a lab artifact has failed. Gazzaniga's later work suggested the effect persists in ordinary life, just without the dramatic testing conditions to expose it. The interpreter theory, his own proposal, argues the left hemisphere constantly narrates a false sense of single authorship over choices it didn't make. If a person can house two decision-making minds without ever noticing the seam, how sure are you that you only have one? Number 4. Near-death experience recall during Flatline EEG. Cardiologist Pim van Lommel was not investigating consciousness. He was running a long-term, prospective study of cardiac arrest survivors in 10 Dutch hospitals, a study of resuscitation outcomes, a routine cardiology follow-up project. Standard neuroscience predicts that consciousness requires active cortical electrical function, and that a flat EEG, showing no measurable brain activity, means no experience is being generated or stored. Van Lommel and his team stumbled onto reported cases where patients described detailed, verifiable events, conversations in the room, actions taken by staff during the exact window when their brain activity registered as flat. Van Lommel published the findings in 2001 in The Lancet, one of the most cited medical journals in the world, documenting that a subset of the 344 cardiac arrest patients studied reported memories they should not have been able to form under the standard model of consciousness. Every explanation offered has run into problems. Oxygen deprivation was proposed, but it doesn't explain accurately reported specific checkable details. Residual microactivity undetectable by surface EEG has been suggested, but no direct evidence confirms it was present or sufficient to generate structured memory. The medical explanation that satisfies everyone still doesn't exist 2 decades later. If memory can form without detectable brain activity, the boundary between on and off for your own mind may not be where you think it is. Number 3. Integrated information theory's panpsychism implication. Neuroscientist Giulio Tononi at the University of Wisconsin, Madison was not trying to argue that thermostats have feelings. He was trying to build a rigorous mathematical definition of consciousness that could explain why some physical systems generate experience and others don't, a formal, almost engineering problem. Standard intuition holds that only sufficiently complex biological brains, or something functionally similar, can have subjective experience. Tononi's framework, built around a measurable quantity he calls phi, representing a system's integrated information, stumbled onto an uncomfortable mathematical consequence. Any system with non-zero integrated information has some non-zero degree of experience, however faint. Tononi laid out the theory formally in a 2004 paper in BMSIC Neuroscience and expanded it substantially in later work through the 2010s. That means, by the theory's own math, a sufficiently interconnected logic circuit, in principle even a very simple one, technically registers above zero on the same scale that describes your own waking mind. Every attempt to patch this away has run into trouble. Restricting the theory to biological substrates only breaks its own internal logic, since phi is defined purely structurally, not biologically. Some theorists, including philosopher David Chalmers, have openly noted the theory implies a form of panpsychism, whether its authors intend that or not. It remains one of the most mathematically serious theories of consciousness in the field, and it was never trying to reach this conclusion. If phi is a real physical quantity and it's never truly zero, is any object you've ever touched completely empty inside? Number 2. The hard problem. Philosopher David Chalmers was not trying to start a controversy. He was trying to formally categorize which questions about the mind were actually solvable, sorting them the way a mathematician sorts a list of open problems. Standard neuroscience, and most working scientists, assume that once you fully map the brain's mechanics, neuron firing patterns, chemical gradients, electrical timing, subjective experience would simply be explained as a byproduct. The same way explaining digestion explains hunger. Chalmers stumbled onto a distinction that split the field. He separated the easy problems, explaining behavior, memory, attention, from what he named, in a 1995 paper in the Journal of Consciousness Studies, the hard problem: why any physical process should be accompanied by subjective experience at all. rather than occurring with no inner feeling whatsoever. Every attempt to dissolve the problem has failed to satisfy critics. Some, like philosopher Daniel Dennett, argue the hard problem is an illusion generated by the easy problems themselves. Others insist that no amount of neural wiring diagrams, however complete, logically implies the existence of felt experience. That you could describe every synapse in a human brain and still not derive, from that description alone, why there is something it is like to be that brain. 3 decades of published work later, the two camps have not converged. Your ability to feel the color red, not just detect its wavelength, remains something physics has never derived from first principles. Number 1. Quantum effects in microtubules. Physicist Roger Penrose and anesthesiologist Stuart Hameroff were not trying to build a fringe theory. Penrose was working on the limits of algorithmic computation, and Hameroff was studying the structural proteins inside neurons called microtubules, routine cell biology. Standard neuroscience predicted that the brain, at body temperature, is far too warm and wet for delicate quantum states to survive. Decoherence, the collapse of quantum effects from environmental noise, should happen in a fraction of a second. Penrose and Hameroff stumbled onto a proposal that broke that assumption, beginning with a 1996 paper and expanded through later work. They argued that microtubules inside neurons could sustain quantum coherence long enough to influence conscious processing, a mechanism they called orchestrated objective reduction. Physicist Max Tegmark published a rebuttal in Physical Review E in 2000, calculating decoherence times in warm neural tissue on the order of 1/10 of a trillionth of a second, far too fast to matter. Every attempt to close the door on the theory has run into new complications instead. A 2014 study led by Anirban Bandyopadhyay at Japan's National Institute for Materials Science reported observing vibrational resonance in microtubules consistent with warm quantum activity, though the field remains sharply divided, and the theory is still considered contested by most physicists. It has never been formally retracted, and it has never been confirmed. If the strangest layer of physics really does reach into the biology inside your own skull, no one on either side of the debate can yet tell you what that would mean for the thing you call you. None of these 10 anomalies live at the edges of science, in some obscure corner nobody checks. They sit at the exact center of our most tested, most repeated, most Nobel-rewarded theories, hiding in plain sight inside quantum mechanics, neuroscience, and cardiology alike. The universe is not confused. It has been running the same experiment, undisturbed, for billions of years. We are the ones staring at a result we can measure perfectly and still cannot explain. Maybe the discomfort isn't a sign that something is broken in physics. Maybe it's a sign that we built our entire picture of reality around a gap we haven't found the courage to name yet. If you want to see more videos like this, click the video on screen now.